Hello. So yes, my name, Keggy the Keg is a handle. That's not my real name. But we can kind of call me that for now. So this is a talk called Words Have Meaning, leveraging LLMs to enhance, insider threat investigation capabilities. I'm Keggy the Keg. I am a digital forensics and incident response. That's DFIR, investigator, engineer, and, sometimes Keg. So, who am I? I've been doing this for over 10 years now. I've been an investigator of cybersecurity and forensics incidents across a range of different environments. I've handled everything from small retail merchants dealing with credit card fraud hacks, all the way up to major nation-state attacks against cloud providers at scale, handling sophisticated adversaries, handling opportunistic adversaries, sort of the whole range of cybersecurity incident response engagements that you can come across in this field. Recently, in my work, I've had more of a focus on insider threats. Insider threats are some of the most challenging to detect and prevent and defend against because an insider has legitimate access to your network already, right? This is not an attack vector where you can rely on watching for external signals or other defensive alerting that would help you kind of understand, am I under attack? These are attackers that are already within your environment and thus have a legitimate reason to be there. Ironically, also, I am more of a scotch drinker than a beer drinker, but that's, So, quick agenda to go over what we're talking about here. The problem that we're going to go over the background, kind of the problem space. There's a lot, this is a pretty niche subject, so there's a lot of background and context that you need to understand sort of what we're talking about here. We're going to go over two different solutions, one that's a naive method and one that's a little bit more sophisticated. Talk about a lot of the caveats and limitations that we encountered when I was building this, and then end with open questions and future research, which I think is actually probably the most interesting part of this talk, in my opinion. So, to begin with, what's the problem that we're trying to address here? The goal of digital forensics investigations is to tell a story, right? What happened? Who did this? When? What data was accessed? Did it leave the environment and how? All of those kinds of questions are important for a digital forensics investigation. Most leaks or insider threats, if you look at the diagram on the right here, follow kind of a pattern. There's some sort of data within the environment that's either sensitive or confidential or otherwise of value to an attacker. They're going to access that data. They're going to retrieve that data to themselves in some capacity, and then either they're going to aggregate that data by repeating the process, or they're going to proceed to exfiltration, and they're going to exfiltrate that data out of your environment. Now, there are many different actors and motivations in the insider threat space, but there are two broad categories that most of them will fall into. One of them is a whistleblower, someone who feels that they're justified in exposing data from inside a company, either because they feel that there is a regulatory need or that there is some sort of public value to them exposing this data. They may do that via a journalist. They may do that themselves, just post it on Twitter or something like that. And the other is for financial gain or intellectual property or IP theft. So that would be someone who maybe they work for your company and they're going to go start a competing business and they want to give themselves a head start, so they're going to steal proprietary data to take with them to give them a head start as a competitor. Now, it's important to note that if the entire trail here, this 1, 2, 3, 4, is digital, there's a high likelihood that we can attribute or alert on this process, right? We can look for things across all of these different stages in our environment through logs, through a mature detection and response program that would enable us to either, if at best, prevent this access, or at worst, at least be able to audit if we see a document that has left or information that has left our environment, trace it back into our environment. Now, what happens though if our adversary is very clever? What they may understand is that they can break that digital chain in a few different ways that would make our lives as digital forensics investigators much more challenging. One of them would be to just take a picture of the screen with the data on it, right? That introduces a change of the transmission medium from digital into a visual medium. right? So now instead of a pure unbroken digital chain, we as the forensics investigators hit a dead end where we can't surmount that gap. They could also read the document out loud to someone, which would be a transmission medium change from a digital to an audio medium. They could also allow someone to look at their computer, which would be sort of a way to provide access without a digital angle to it. So this can be very frustrating in any sort of investigation, because we as the digital forensics investigators have to tell clients, executives, lawyers that we're working with that we just don't have any way to identify this, that this is a dead end for our investigation. But the good news here is that the information content still needs to survive this transmission medium change, right? If I read you a document, the information in that document still needs to go across that transmission medium change relatively intact for it to have value to you or to me as an attacker. So the question ultimately becomes, how do we trace information content to survive that change in medium, right? How do we add things to that information itself such that even with a transmission medium change, we can actually still continue our investigation? Now, in the current space, there are ways that you can try to assist with insider threat investigations. The two main technologies or kind of portfolios here are DLP, or data loss prevention, and watermarks. DLP is typically a suite of digital proactive and detective controls. An example of this might be a DLP solution that has an ability to either monitor for or disable peripheral usage, right? So if you've ever been in a company and you plug in a USB device and it says, oh, hey, this USB device is not approved, please go talk to your IT administrator. That would be an example of a DLP solution working, right? It's trying to either prevent people from using USB devices entirely or only allow specific traceable approved USB devices to be used in an environment. Another thing that you can use, there's also a tool called UEBA, which is User Entity Behavior Analytics. Those use machine learning to develop a baseline for what is a user normally accessing, and then they can develop, do basically basic anomaly detection to say, all right, the user's behavior typically looks like 9 a.m. to 5 p.m. they're working, they're mostly submitting PRs on GitHub, and maybe they're responding to a Jira ticket or two, and then the next day, they're suddenly accessing your wiki 100 times. That's a very unusual change in behavior. The UEBA would flag on that, it would alert it to security. Security could then say, something's wrong here, we need to do further investigation. Watermarking is sort of the other major category here. Watermarking is actually a very old technology. It goes all the way back to the Romans, the medieval ages. People would use it for integrity of messages, typically not necessarily for auditing of messages. But in modern times, a lot of what it's used for is tracing the provenance of a particular piece of information. And so an example of this, there was an article that came out a few years ago where Tesla admitted that they were using spaces after sentences to encode information about a user so that if that document were exposed or leaked in some way, they could identify who leaked it based on reconstructing the number of spaces after a sentence and say, oh, okay, there's data encoded in here. We know that it was this individual who leaked it to the reporter or press or what have you. There are other methods that you can do that. It's not just spaces. You can use any sort of presentational adjustments, right? You can do font injection where you use Unicode fonts to modify certain parts of words to encode information. You can use alignment where you put it on the page with slightly different margins that are imperceptible to the user, but if you were to actually analyze it on the other end of it, you would actually be able to see, oh, this margin is, 2 millimeters smaller than that one, and that means that it was someone over here. The only thing is, all of these methods are not addressing the thing that we discussed in the previous slide, which is none of these actually affect the information itself. So, if there's a transmission medium change, none of these methods can really help you. There's also another complicating factor here, which is, if you're using spaces or encoding or things like that, what happens if only a portion of your document is actually leaked? An example of the necessity of the entire document would be, if you're familiar with the case of the intercept and reality winner, Reality winner was a worker in the United States National Security Agency who leaked a classified report to a press agency. And she was discovered, if you look over on the right here, using the tiny dots that a printer actually encodes in the page when it's printed out. And The Intercept posted the entire document that she gave them on their website. That's actually the actual dots from their website. And they exposed her that way because they gave the entire document, they gave access to the entire document, which led the investigators basically right back to her. But what can happen is if a news agency receives these documents, they might only publish a quote from that document. They might not publish the whole thing. As a result, if you only have a fragment of that document, now maybe the dots don't show up. Maybe the spaces, there's not enough of them to actually uniquely identify a user, right? So you can't rely on a single document level watermark or even watermarking scheme across an entire document in order to actually tag that. The good news here, and this is where we get into sort of the solutions that we've developed, is parsing for criticality to the overall document is actually a strength of large language models for parsing for relevance, parsing for semantic context. So just a quick background here for anyone who's been living under a rock since 2022. In 2022, ChatGPT came out, which was sort of the first public exposure to large language models. Their areas of strength, as we mentioned, parsing for semantic meaning. They create output text that can presentationally be, that can pass for native speech, right? For the most part, their generation is stochastic in the default configuration. There are ways you can change that, but we're not going to go into that. The non-deterministic nature in a lot of areas makes it challenging. You've heard about hallucinations from a lot of companies or vendors. These are issues that are known with large language models. And there is a whole field called mechanistic interpretability, which is the effort to understand exactly at the neuron level within large language models how they work and kind of demystify the internal workings of these systems. But that's outside of the scope of this talk. So the question then becomes, how can we leverage these to watermark that information, right? How do we leverage these to actually change the information that we're going to use in such a way that we can actually recover data about its provenance on the other side of a transmission medium change? So in the first method, I simply looked at it and said, all right, let's do two phases of prompts. We're going to basically prompt an LLM to identify the most important sentences or semantically critical segments of a content, right? In this case, a confidential document. And then we're going to prompt the LLM to rewrite each segment of that. And we're going to, for each version of that sentence, we're going to then tag it with either a user or a group, depending on the amount of variability that we can make the LLM give us for that particular sentence. Then we're going to store the rewritten segments and corresponding tags as entries in a database. We've got one segment per table, and so then our database for the document has several tables, each involving each containing a key value pair, where the key is the username and the value is the rewritten sentence. In an investigation, then, if we come across any one of these sentences, right, even if it's just a quote, we can go back to our database and say, all right, what user is that corresponding to? And we now know uniquely that user was the person who leaked that document. These are the prompts that were used. This was tested initially back in January with Senku 7TB. It was also tested later over the summer with ChatGPT 4.0, with Llama 3.1, and then Claude 3.5. Most of these, I'm not going to go into the specifics here. I can talk to you about the results later if you want offline. The ultimate answer here is that most of these produce basically the same results. There's not a significant variation between these in terms of results of how they actually analyzed the semantic content or how they were rewriting sentences. In terms of the only real thing that I noticed in terms of kind of prompt manipulation was that the more forcefully and aggressively you tell the LLM to really try to rewrite the sentence, the more combinatoric space you can open up. So you can see that over in phase 2 with sort of the different prompts there. Now, there are some drawbacks to this first method. As I mentioned, this is the naive method of just sort of, let's just rewrite the sentence, tag it to an individual. One of them is the combinatoric limitations. There are only so many ways, at least within the English language, this was all conducted in English, there are only so many ways within the English language to rewrite a particular sentence without losing the meaning of that sentence. And so, especially if it's a short sentence, you're not going to get a lot of combinatoric space where you could have, if you have a company of 4,000 people, you're not going to be able to rewrite a single sentence 4,000 ways. As a result, this is not going to scale significantly beyond a handful of unique tags, which means you might have to then settle for using it to bucket your target pool into something that's more manageable. So you might not be able to say uniquely identify a user with this method, but you might be able to say, well, it was someone from a particular department who leaked this document, right? Which narrows your subject pool and then helps your investigation because you're not looking across the entire company now. The other thing is obviously storage inefficiency because we're storing the entire rewritten sentence for each segment, for each combination that we're possibly doing. This can result in a fairly large, large size of the database, and we're not storing it terribly efficiently. As a note at the bottom, we could add to our prompt additional ways to rewrite the sentence. We could, or add other things that could expand the combinatoric space. An example here is we could add add one misspelled word to the prompt is something that we could do. But that really doesn't get at the root of the problem, which is this is still pretty inefficient. So, we move on to our next method, which is, let's continue with our idea, but let's see if we can improve upon it a little bit. And so we start the same way, which is using the LLM to identify the semantically relevant portions of the document, the portions that are most likely to show up in a quote, the portions that are of most value to either an insider or an attacker. But then instead of prompting the LLM to rewrite the entire sentence, what we do is we prompt the LLM to identify candidates for replacement within that sentence and give us a range of options for each of those candidate replacements. So in the example here, we have two words within a target sentence, pivotal and moment. We've asked the LLM to give us as many candidate replacements as it can come up with, and that gives us 5 additional words that we could use. And then for moment, it came up with 3. So we have now a combination space of about 6 times 4, which is 24. So for 2 words, we now have 24 different permutations that we could use. Now, then from there, what we can do is now each rewrite can be stored as an encoding rather, as a series of indices into an array rather than as a naive, just rewritten sentence stored in some sort of, stored as a key value pair. And so each encoding now is much more efficient. And also what this lets us do is each of these encoding sequences now, because we have a sequence of permutations as opposed to a single sentence, we can identify patterns within that. So even if we get a partial sentence, we can now look and see if there's an encoding pattern within that, which helps us narrow our target pool to from what it was. So after we've performed this encoding, we actually add a further step here, which is to perform an additional layer of LLM analysis by prompting the LLM to make sure that our sentence still makes sense with the permutations that we've selected. So if there's one where maybe just in natural English language, it wouldn't make sense to have these 2 words next to one another, then the LLM can detect on that, alert us, and then we can remove that particular encoding and either select another one or move on. And then in the investigation, we work the same way as before. If we identify the sentence, we translate it back into the encodings and identify a user or target pool based on our encodings. Here's an example of kind of like a visualized example of a very simple version of this, of what it would look like, right? We have 3 words here that the LLM has selected as replacement candidates. It's given us a list of replacement candidates. And then when we are building our encodings, we're simply building different combinations of these different replacement candidates. So as I mentioned, the first segment here is actually the same. So the prompt is the same. In method 2 here, we have a different prompt for actually identifying the replacement candidates, which is this prompt here, which is basically, you're a linguistic expert. Tell me what words could be changed without altering the meaning of the sentence, and then respond with a JSON array of those words. This is the only notable differences here in terms of the responses when I tested this across multiple LLMs. In some cases, the LLMs will return empty arrays. They'll just return every possible word, and then they'll just return empty arrays for words that they can't identify an immediate replacement for. And then for other ones, they'll only return arrays for words where they were successful in able to actually generate replacement candidates. So that was the big difference that we noticed there. So there are obviously some caveats to this method. One of the biggest ones is these techniques are all vulnerable if one actor can possess two people's version of the same document. So if a reporter were able to solicit the same document from two different sources within a company, they would receive two different copies of that document, and they would actually be able to hold them up to one another and say, some words here are different, this quote is different, these sentences aren't lining up as the same. This could happen this could also happen innocently, right? In terms of, it could happen by an error. In one case, at the Tesla example from before with the spaces, that was actually torpedoed by their own legal counsel, sent a copy, their personal copy, to the entire company, in addition to the copies of the email that everyone had received. And so what that meant was everyone received an individualized copy with different spaces after the words, but then the legal counsel sent their copy, which had different spaces after the words. And so individuals were in the company were able to hold up both versions and see that the spacing was actually different. And that led to some moderate outcry among employees who realized what they were doing. You could also see an issue where if someone were sharing their screen, right, and showing a version of a document, if someone else had that version opened locally in the same meeting, they might actually be able to determine, oh no, the version on that person's screen is different from the version that I have locally on my machine. Why is that? Now, it's also important to note, this is not necessarily unique to the semantic watermarking technique that we're talking about here. Physical watermarks also have a similar issue, right? If you were, like, as I just mentioned with the Tesla case, this is something that you could, if you have two versions of two different watermark documents, you could notice that there are differences. So this is not a unique issue here. And also, the identification of the watermark, as I point out at the bottom here, can be a deterrent factor. If that journalist gets two copies and they don't understand why the documents are different, they may be deterred from either publishing quotes from that or from publishing the story in the first place because they don't understand the veracity or the actual, whether the documents are true or not. So there can serve a deterrent technique there. Another important caveat to note is this is only really important when the information is the thing that has value. And so if you look over at the side here, I sort of drew a little rough diagram where you have information as a broad category and then you have data and content, which are sort of dissimilar categories within that area. And for data, where precision is very important, this technique is not going to be as effective, right? Because you can't really modify the content itself without changing its value at that point. If you have code, if you have design specifications that are very specific, if you have engineering data, sensor data or something like that, you can't really change that because then it becomes useless. But on the other hand, if you have content, which, we would refer to as documents, marketing plans, sales plans, strategic documents, things like that, that's where this might be a much more applicable technique. If the structure reform is critical, you're not going to get as much value out of these techniques. Additionally, if there are legally sensitive documents or legally privileged documents, that's an area where something like that, where the content is important, may also have precision needs. Lawyers may be very uncomfortable with an LLM randomly changing words in a contract, for instance, or something like that. That may have ramifications that you would have to discuss with legal counsel prior to implementing any sort of version of this technique. Now, from an implementation perspective, there are sort of two broad areas that you could implement this at. One would be at the application level. So if you have some sort of document repository, whether that's a wiki or a messaging system, or maybe you have a learning management system or knowledge management system of some kind, centralized storage for documents, you could implement that at the application layer as a plugin, right? So you could implement this as something where on access to documents, this is rewriting the content and passing it to the user. This enables also the pre-compilation of marked content, right? So you don't have to spend as much compute power other than on access tagging who accessed the document and making sure that the unique version of it is tagged to that user. It is more transparent to individual users this way also. They're just going to be using the same system that they would normally be using. They're not going to have to interact with anything outside of what they would normally do. And it's also more robust against efforts to circumvent the use of this system to mark documents because it's all happening on the server side, on the back end. Most employees are not going to have administrative access to those systems to view the raw documents or the raw data. They're only going to be accessing it through the front-end UI, which would be giving them the data that this plugin is reflecting back to them. You could also implement this on access by interposing this system between the data source and the targets who are accessing it. One way to do that might be if you have sort of a man-in-the-middle proxy of some kind already for deep packet inspection already in your environment. You could leverage that at this layer to actually modify the content in transit on its way to the user. You could also, depending on the level of maturity of your environment, if you have enterprise controls around web browsers, you could force a browser extension, which would implement this at the browser level when it's rendering content that needs to be marked. This is more vulnerable to circumvention because it's client side, obviously. If you have developers who have administrative access to their machines, they might be able to disable browser extensions. They might be able to otherwise modify their access patterns in ways that would avoid this particular content. So, moving along to open questions, the read-only nature here is obviously a significant constraint. Because if you have two people accessing the same document at the same time, they can't, this technique can't happen because they can't see two different versions of the same document and be openly collaborating on it. Especially in modern office environments where you have tools like Office 365 or Google Docs, which are highly collaborative, this is a pretty big sticking point. You're not going to be able to use this to, in those environments unless you've locked the documents. So this is only really useful for sort of formal documents that have been locked for editing and are only being accessed in read-only. It means as an open question, is there a way to leverage this technique to actually use it in an environment where two people are accessing the same document? I don't have a good solution to that. So I'm curious if anyone wants to come up to me and have a chat after that. After the talk, if they have ideas for how that might work, I'd be very curious to hear about it. One other method that I considered but was too complicated to build in the time that we had was using real-time audio and video to in concert with this technique. So if you had, for instance, a presentation being given by a CEO that was particularly sensitive, you could actually use generative AI to modify the audio and video as it's being given by the principal. And so what this could look like, if you look on the right here in the diagram, you could say, have the CEO saying something, and then you could parse that into text, have this run this against that text to modify it for an individual user, and then use generative AI to rebuild what the person is saying with the new text that's been watermarked, right? So that way, if someone just leaks out, oh, hey, I heard the CEO say this thing, now you know who said that. The current hardware requirements for that are probably not sufficient for real time, but we're moving there, both in terms of model efficiency and in compute efficiency. So this is definitely something that we could look out for, in the future. So, in conclusion, I think I don't know if, hopefully people have realized this is not, something that is probably likely to be terribly applicable in its current form. This was mostly a research project to see, is this possible? If so, what are the drawbacks and considerations, and where could this take us, from an insider threat investigations perspective? There are significant limitations, the biggest one being the perceptibility, of the modifications to the content. And then also from an implementation perspective, it's it's still very, very complicated. There's no turnkey solutions for this. This is not something that you can just buy from a vendor if you're a company that wants to implement this. You need to develop it yourself. And it could be computationally or financially expensive because of the amount of, marking required. Additionally, depending on how which LLMs are you leveraging for this, there may be data privacy issues because you're using this on your most sensitive documents. And so if you're giving that data to OpenAI or someone like that, they may be now training on your sensitive data. You would have to have some pretty significant legal controls in place about how you're using these LLMs. On the strength side, though, fundamentally, this does answer our initial question of how do we trace data over a change in transmission mediums? This does perform that goal. We are able to maintain a watermark that goes across a transmission medium change and then uniquely identify individuals on the other side of that transmission medium change. For small orgs where you have a limited target of confidential data, it's probably not terribly valuable to you, but for a large organization with a lot of sensitive documents and a rigorous document management system, which are usually read-only, this could make sense as a plugin for that kind of a document management system. And I'll close on saying the best uses of this are basically one-way communications to a workforce or to a lot of different users in a read-only fashion. So it could be an email to an entire company or something like that, where the target space would be very broad from an investigative perspective, but it would be challenging to understand uniquely who made that document leave or content leave the environment. All right. And that is it. Thank you so much for your time.
Thank you, Keggy. Should we just call you Keggy or Keggy the Keg?
I can go by either one.
Okay. Round of applause, please. Thank you. Have we got any questions for him? Yes, please.
Hi, sorry for my ignorance. I didn't catch the first slides of the presentation, so please correct me if I'm wrong. Is this thing the thing that are going to protect the data privacy of the user by changing the text inside the leaked content? And the second thing is to narrow down the adversary or the threat actor inside the company who's the culprit that upload the document outside. Just two questions.
Yeah, so I'm not sure if I follow exactly what you're asking, but maybe this will answer the question. In terms of what this is after, yeah, I think you're right that it is about uniquely identifying or where possible, limiting the suspect pool, right? So if you have a document that's shared with 200 people and you can watermark this in a way that breaks that 200 people into groups of 10, right? Now your suspect pool has gone down an order of magnitude from 200 to 10 people that you need to investigate. In terms of uploading the document, this is designed more for scenarios where we don't have a digital trail. If someone is uploading a document, there are a lot of other digital ways that we as cybersecurity investigators could identify that activity. We could use DNS logs, we could use browser history, we could use all sorts of different, we could use network connection logs if we have, actual NetFlow logs on our environment. So we could use a lot of different digital aspects to actually investigate that activity if they were uploading it somewhere. But this is more about specifically if they use a technique like that I mentioned earlier in the talk called a transmission medium change, where they're not sharing it in a digital way, right? They're reading a document to someone, or they're taking a picture of their screen or something like that. Does that help answer your question?
Yes, cause I first thought that the leaked document is already published, right? Published online, and then you try to trace back, who's the culprit that spreads the document.
Exactly.
Inside.
Yeah, and that's a good point. In some cases, you may the document may be published online. In some cases, the article may be published with a quote from that document. In other cases that I've been personally involved with, your company may get an email from a reporter, which is called a request for comment, where they basically say, oh, we have access to some documents. We're not going to tell you what they are, but here are some quotes from those documents that we're going to use in our story, and we would like you to confirm that these are accurate quotes, effectively.
Okay. Thank you.
Cool. Any other questions? Okay. If not, then thank you again, Kegi, for your wonderful presentation.